Okay, yet another example for class 14. Not sure how many people will watch this for my class, but I thought it was a good thing to include. We might refer back to this example when we get to chapter 14 that covers some turbo machinery. But this is a Francis turbine. By the way, this comes from Crow and Elger's Engineering Fluid Mechanics, the 9th edition. And this is an example from their book where power delivered by a Francis turbine. And a Francis turbine is shown in the diagram, and water is directed by guide vanes into the rotating wheel, which they're calling the runner, of the turbine. The guide vanes have a 70-degree angle, and once again, that's not always the reference that I would use. Sometimes I would use the complement of that, so it would be like 20 degrees, but that's the way they decided to go. 70-degree angle from the radial direction, and water exits only in the radial direction, right? So it pours straight down as you're seeing in the side view of this. The outer diameter is 1 meter, and the inner diameter is 0.5 meter. The distance across the runner, that's this guy right here, is 4 centimeters, so that's actually pretty small, right? The discharge is 0.5 cubic meter per second, and the rotational rate is 1200 RPM. The water density is 1,000 kilograms per cubic meter. And we want to find the power produced by the turbine. And so here's a little picture of a Francis turbine. Here's a bigger one, so you can kind of see where we have water running through here. And it's kind of looks a lot like the opposite of a centrifugal pump, right? It's kind of interesting, right? But let's take a look and work through this problem. So let's see. They gave us the flow rate. So let's. I'm just writing it down, I guess. All right, that's what I'm doing. Let's find the mass flow rate then. We'll take the density times the volumetric flow rate, and that's going to be 999 kilograms per cubic meter times our 0.5. We should be able to do that in our heads. It's close to 500 right there. So kilograms per second, sure. And I'll go ahead and do my FBD. I didn't do that in the previous examples, but I kind of like it. Where we're going to have here's our little FBD, and here's our flow FBD. And so now we're going to have a velocity coming in that way and a velocity coming in here. And so here's the radial one, and here's the tangential one, right? So it's actually have a velocity, a real velocity coming in from the real world is this direction right here. We could call this the V1 coming in. So this velocity right here is going to just help us figure out what the mass flow is, and this is the velocity. That's really the r crossed with the velocity. Remember, that's the if we go back to what we were using or where this equation came from, right? This equation actually comes from right up here, right? We have r crossed with v. This is really the tangential one. And this is really the radial one here, or it could be the relative one, right? So we had to be kind of careful. But this is the mass flow velocity, but this is the tangential velocity, the one that we would use with Euler's turbine equation right here. We use the tangential velocity for that. So keeping in mind whence this came from. So here on let me put the torsion, the torque that's onto this thing over onto this side. And this thing is coming out completely in the radial direction. And by the way, this is happening everywhere along here, right? It's coming, I'm only drawing in at the top, but all these velocities are coming into there. And this is the radial direction is coming inwards. You know, they're all coming inwards towards the center, just like it shows up here, right? So I'm just not drawing all of the arrows that would be in here. I will have some stuff over the side that I might want to work on before I do over this. And so I might want to have the area of this band on the outside, right? So this area of the thing coming in, because I know the flow of here, so I can find my radial velocity coming inwards because of that. So I'm going to get this area first, and I'll go, it's going to be pi d1 h, where I'm going to call this h right there. So I guess I wrote it underneath there, pi, and this is 1 meter, and the h was 0.04, right? Yes, because there were centimeters. I don't like centimeters. 0.1257 square meters. So my velocity in the radial direction, 1, is going to be my flow rate divided by that band, right? So that's going to be the perpendicular to the area velocity. And that ends up being 0.5 divided by the 0.1257. So we have a radial velocity of VR1. Oops, excuse me. Just write down the number. 3.979 meters per second. Almost went to feet. And now because we know that, and we know this, and we know that angle right there, we could take the tangent of that angle, and I'm trying to see, this is going to be the run, and we want the rise, right? We want the leg that's opposite from that angle. Therefore, we will multiply. So we can get the tangential velocity of the thing coming in as going to be VR1 times the tangent of the angle provided, or 3.979 times the tangent of 70 degrees. And so that's going to be a larger number, 10.93 meters per second. And because this is we don't need to do a velocity triangle here, because this is the actual tangential velocity, not the relative tangential velocity. So it's going to be okay. That one right there, I had to double check and rethink, and I'm not going to tell you that I knew that right away. I hemmed and hawed about what whether it was going to be the relative one, but because this is an actual velocity, as seen by, let's call it the inertial reference frame, I was okay with this. So this is going to be, I'm tempted to write it out this way right here again, where we say out and then r m dot v, let's call it tangential, minus in r m dot v tangential, right? Or we could write Euler's turbine equation. And we'll get the same thing, right? We'll find out that we have a torque is going to be, so where's Euler's thing is going to be m dot and r1v tangential 1 minus r2v tangential. No, I'm sorry. No. Okay, so I'm going the other way. So this would be 2, right? Let me double check with what I had written down. I'm sorry. I don't want to write the thing wrong. Yeah. So that's what we said was the 2 minus the 1, right? Which is the same thing as the out minus the in. But here we have in, right? So this is the in right in there. So we actually have a minus coming into there. But noteworthy up here, this is going to be minus. So it's going to end up being minus. That doesn't account for an Euler. I think that they're not really deciding which directions these are going to go. But so this is in a side, but over here, I'm going to use up here to this actual equation. And there's the torque that's happening onto here. I'm trying to decide whether I want to do the sign conventions that way. Yeah, I think I can. Yes, I think that's fine. So I had positive over here, and I decided to go with this out is 0. This is the outlet right here. And the inlet, we will go the radius. So that's going to be 1/2 of the, all right, so because it's coming from the outside in. So it's going to have a 1 meter divided by 2. Sorry, I'm trying to think my way through there. 1 divided by 2. And the mass flow we found up above is 499.5 kilograms per second. And the velocity we just found to be 10.93. And I just said that because it's negative because it's going in there, but it's negative here because it's a negative moment right there. So I think it goes plus. So we have right here, I have that as 2,730 Newton meters per, no, not Newton meters, excuse me. And then for the power, we want to have the torque times the omega, and we said that we had 1,200 RPM. I guess I'll go ahead and put this in the same formula here. So it's 2,730, and then the RPM is 1,200 revolutions per minute. So we want 2 pi over 60, and what we're left with is a large number, because we are 343,100 Newton meters per second, but the power that we can extract from this is 343.1 kilowatts. And I'm trying to think about the signs involved right here. All right, so let me think about this. This thing, yeah, that's correct. All right, so the torque that's applied to this should be positive. That's right, because it is going in the torque is going in the opposite direction of the omega, and that means that what we will have now is we will have power extracted right here. So this is extracted power, so it would be overall negative. Yeah, that if we were talking about the sign conventions when it comes to like say energy in and energy out, those would be correct, right? So okay, so it makes sense. This is a counterclockwise torque of the output shaft onto the free body diagram, because these are external moments acting onto here. So yes, that makes sense. So that was another example using a Francis turbine. Let's go to a Pelton turbine in the next example.